Hello, my name is Nick Materise, and I'll be presenting tunable capacitor for superconducting qubits using an indium arsenide, indium gallium arsenide heterostructure. And this work was performed with the support of the Army Research Office, as well as the National Science Foundation and the Graduate Fellowship for Diversity in STEM. My advisor is Elliot Caput at the Colorado School of Mines, and our collaborators are at the Center for Quantum Phenomena at the Department of Physics in New York University. So I'd like to start by comparing both a voltage-controlled coupler with a flux-tunable coupler. And the voltage-controllable coupler that our collaborators will be talking about, not a voltage-controlled coupler, but a gate-mon-like qubit, so a voltage-controlled Josephson junction, are in these two talks that were given during the APS March meeting 2021. And I just want to discuss the two benefits and disadvantages of these two couplers. So the voltage controlled coupler, what this entails is you apply some sort of gate bias to a semiconductor, and it changes the coupling between two qubits on either side of these capacitors. Whereas here you apply some sort of flux bias from an external magnetic field. This coupler is first order sensitive to this flux bias. Well, this one is second order. So we expect this one to be more sensitive to flux bias compared to voltage. We don't expect any heating from our voltage bias, whereas current biases can heat the system. As well as this model, we expect less crosstalk versus more crosstalk from straight magnetic fields. Unfortunately, this is not part of the circuit QED stack, whereas this one, is part of the compatible with circuit QED. And we expect there'll be high dielectric loss in the 2D electron gas that implements this coupler. And so the effort in modeling this device involved something of this sort of stack where we have 3-5 materials defining the 2D electron gas. So this is our heterostructure, as well as some sort of buffer layer, typically a graded buffer layer, but here we're just fixing the concentrations of indium, aluminum, and arsenic. And then we have these two air gap capacitors here given by these epsilon naught, as well as gate oxides, silicon oxide, so very lossy oxide, but again, we do this as a rough design for our coupler, as well as gold contacts. And so what we did was we calculated the electron densities for the equilibrium solutions, meaning that we did a COMSOL simulation. We include the full Fermi-Dirac statistics, and from the equilibrium solutions, we inferred what the essential electron densities would be in these regions when we apply gate bias or not. Now, when we do this kind of simulation, we apply gate biases to none of these. So we ground all these terminals versus we ground these two and we apply negative bias here, and then we apply negative bias on all three terminals. And the idea is that the capacitance that the two qubits see on either side of these air gap capacitance changes as we deplete the two deck. So as fewer electrons are concentrated in this region, we then have something that looks more like an insulator, which behaves like a larger capacitance. And so we can tune between a small and a large capacitance based on the applied voltages on either of these gates. And we can sort of localize where we would have charge based on if we ground some of those terminals or have different gating patterns. And so this was demonstrated in other kind of 2D electron gas architectures for various applications in quantum dot qubits, as well as these gate-mon, so gate biased Josephson junctions. Now, from here, we inferred a simpler geometry. So we have three different limits that we'll look at. We'll look at the fully conducting limit. So this is where the gray regions are conductors. We have fully depleted limit for the single gate case. And then we have the fully depleted in the 3-gate case. And this is how we'll be able to extract the capacitance matrix from a DC calculation, a static electric field calculation, as opposed to what we were doing in the simulations that included the full drift diffusion model for semiconductors. Now here we'll just solve Poisson's equation, which is given here with the continuity equation in 2D. So charge conservation. And then we extract the capacitance matrix, which relates the voltages on each one of those terminals to the charges. And the ordering for these voltages is such that if I go back to the previous slide here, we label this 1, 2, 3, 4, 5. So the focus will be on terminals 1 and 2. That's the capacitance that we want to control. And so here we can see in these two plots, one, the matrix elements for the fully conducting case, and two, the fully depleted case for all three gates being used. And what we see is the difference, the ratio between the fully conducting and the fully depleted limit is on the order of 160, which is great. That gives us more than 2 orders of magnitude tuning that we expect in the capacitance, which in turn should then give us 2 orders of magnitude in the coupling between these two qubits. And we'll show that later on once we extract the coupling. We see a similar behavior here, although the difference between the conductance, so the conductance being the inverse of the resistance. So a large conductance corresponds to a high conducting region versus the lower conductance is a depleted region or more capacitive or insulating. And so to do this, we extract the admittance matrix, which is a combination of the conductance as well as the capacitance. And these capacitances agree with the DC results that we reported on the previous slide. From here, we went on to estimate the dielectric loss. And so what I mean in the context of superconducting qubits is we want to be able to relate the loss to the expected lifetime of these qubits, the T1 time. So the limit on the coherence based on relaxation into the ground state from an excited state, for example. And this expression here includes all of the contributions from dielectric loss as well as other loss mechanisms. And so we relate the participation ratio, the ratio of the electric field stored in a given region of that device compared to the total electric field in the entire device. And so we relate this loss tangent, we give these as weights on the loss tangents or the quality factors for each one of those materials. And here we see that we are limited indeed by the silicon oxide layer. Further experiments will be able to give better estimates for the loss tangent as well as the participation ratios for these 3-5 materials, which up until this point have not been available in the literature, apart from the work done by Corey Ray-McRae and others earlier last year, or late last year, early this year, where they were working with a tri-layer material that was a aluminum, gallium arsenide aluminum tri-layer. So we'll be using similar techniques to measure those losses in these thin films to be able to estimate the limit on the coherence for this device, apart from the silicon oxide gate oxides. And we may end up changing this oxide based on further investigations. Now, to extract the matrix elements, this is how we're going to be able to discuss what we mean by coupling. So how strong can we couple these two qubits? How easily can we exchange energy between qubits, and how easily can we do 2 qubit operations, which is the limiting operation for modern scalable quantum computing architectures. And so what we did is we modeled a more complicated geometry where we sort of said, okay, we know what the capacitance is as a function of the gate bias, and we know what the 2 limits are on and off. Let's just model that as a lumped impedance. So just a lumped capacitance, this little rectangle. And then we model the rest of the 2 qubit device as accurately as we can to what we would expect to be fabbed in a real system. And here's what the modes would look like in that system. So the electromagnetic modes. So we extracted that from HFSS. Then we extracted things like the quality factor for each one of those modes, the frequencies, as well as these matrix elements, which will be using the diagonal elements as a measure for the capacitances in the Hamiltonian that describes the energy in the system. So now this is the Hamiltonian that we're trying to do. So here's the effective circuit model for our device, and here's a modified circuit model and the Hamiltonian corresponding to it. And what we'd like to extract is this capacitance, the inverse of this capacitance matrix, which gives us the charge-charge exchange interaction matrix elements. And those matrix elements are shown here, and the ratio between depleted and conducting is shown again to be on the order of 2 orders of magnitude. And so we'd just like to summarize that we've been able to show that capacitive couplers are a drop-in replacement for their inductive counterparts. We demonstrate large on-off ratios. We currently are limited by dielectric loss, but again, we want to look at that in more detail, studying the loss mechanisms in these 3-5 materials. And we think this opens the door for semiconductor, superconductor hybrid systems. Also, I'd like to acknowledge the funding sources that I said in the beginning, as well as useful discussions with all these folks. Thank you.